So, good morning, everyone. I will be presenting the work Ultrametric Integral Cryptanalysis, which was a joint work between me and Tim. Before I get into the Ultrametric integral part, I will just talk about integral cryptanalysis in general, and then we can build up to what we actually want to accomplish. So, the term integral cryptanalysis was introduced by Knudsen and Wagner in 2002. And it was, in a way, a generalization of a classical attack on AES, namely the square attack. And the idea behind the attack is that you kind of construct some input set, which can saturate components of your block ciphers. So if you know AES, you have the S-box layer, and you kind of just try to saturate S-boxes in there, and then propagate this information forward. So, and this is some abstract representation of this attack. So each grid corresponds to, well, the AES matrix, and then each arrow corresponds to a round function. So if we here saturate this single S-box, then we still have saturation after the S-box layer. And then, so we shift the rows, we mix columns, and what we then get is that each individual state here is saturated. And you can repeat this again, and then basically each individual state byte of the full AES state will be saturated. And then this property, so this saturation on each S-box, can still be propagated like one more S-box layer. But then in the end, you have a linear layer that will completely break this structure. And the thing that kind of still holds is that if you sum over all the kind of states in your saturation, then you will get 0. And because, well, the linear layer is a linear function, the output will still sum to 0. So every output byte will sum to 0 over this input set. There is a similar kind of technique that's significantly older, called higher order differentials. And the idea there is that if you have a low degree function, you can just take an affine subspace, which is of higher dimension than the degree of this function, and if you sum over it, if you so evaluate and then sum over the outputs, you also get kind of a zero sum property. This is of course all over F2. And like there is a recent line of work which kind of merges these two approaches, where we use algebraic properties of the component to propagate more information through the cipher. And the idea is kind of or the final idea was that you can track which monomials the kind of input set will sum to 0 over, or similarly, you can also just kind of try to track the algebraic normal form or the algebraic representation of the components backwards to the cipher. So there's one big problem with this, and that is that all the recent consolidations are defined over F2. So the only kind of property we can describe are zero sums over F2. On the other hand, the original integral cryptanalysis had these saturation properties. Like in the end, you end up at zero sum, but in between you had saturation. And this on its own is a significantly stronger property, because it basically implies that a single output bit will be 1 half of the time and 0 the other half of the time. And kind of, there is also this folklore of properties that exist where a specific output bit will be 1 over an input set, not a multiple of 2 times, but a multiple of 4 or a multiple of 8 times. So you kind of get divisibility by higher power of 2s. And we did like a quick experiment on present where we saturate a single S-box, and then we got that after 4 rounds, there are indeed some bits which seem to sum to a multiple of 4 every time. And later on, once we introduce the necessary machinery, we will also be able to prove that this is indeed the case. So the goals for this work will be to understand and analyze these divisibility properties beyond just divisibility by 2. And in this way, we want to improve our understanding of integral cryptanalysis. To do this, we will introduce ultrametric integral cryptanalysis, and it is kind of built up of 3 main components. So first of all, we have we construct our theory within the geometric approach. And for that, we kind of define a multiplicative analog of linear cryptanalysis. And then finally, we will ditch the normal absolute value over the rational numbers and use a two-adic absolute value to be able to capture these divisibility properties. I will introduce each of these topics first, and then we'll get into ultrametric integral cryptanalysis. So, the geometric approach. In kind of this presentation, I will keep to the one-dimensional case, where the idea is that many cryptanalytic properties can be described in a kind of two-step process. You design or you define some, or you assign some weights to every input. So then you get like a big vector of weights, and you propagate this forward through the cipher. This propagation of the weights assigned to each vector we call the push-forward operator, and this is a linear operator on these vectors. Then, when we propagate this forward, we can then take a linear function of this output, and that then gives us some distinguishing value of our block cipher. This push-forward operator, its matrix representation has some interesting properties. So this matrix is called the transition matrix. And if we have the composition of functions, then we can write this out as a product of the transition matrices of these functions. And similarly, if we have the parallel application of two functions, we get the tensor product of the transition matrices. Now, there is kind of a dual way to look at this. Instead of propagating input sets forward, we can also propagate these linear functions on the state backwards. And this defines the pushback operator, and it also has similar properties. And this pullback operator kind of encompasses, is also a linear function, and is kind of comes down to composition with your function f. So this on its own is not very practical, but then what we can do is we can try to define a different basis to analyze these transition matrices in, so that certain components of our ciphers become simpler to analyze. And so one, like the best example of this is linear cryptanalysis, where we try to diagonalize or simplify and just diagonalize the translation. So this comes down to key addition, basically. So using characters, we can basically find a basis of linear functions and then a basis of vectors which do indeed diagonalize the translation. Changing to this specific basis gives you what we call the correlation matrix. And this correlation matrix kind of contains correlations of all the linear approximations over your function. And as you can see here, indeed, we do diagonalize the addition. And some other interesting tidbit is that these bases are orthogonal, or this basis is orthogonal, or almost orthogonal up to a factor 2. And that's because like the translations basically form a group. And later on, we will see that this is not the case, and this will slightly complicate our analysis. Then this correlation matrix also has similar properties to the transition matrix. So you still have the product of matrices for composition, the tensor product for parallel application, and additionally, linear maps become really simple in the correlation matrix. It's basically just a permutation, or if it's an invertible linear map, it's a permutation matrix that just acts on the different basis elements. Then, using these properties, we can start analyzing functions. So many block ciphers consist of a large number of round functions, which are also individually split up into components. So we can split our function up in a large number of components and write it out as a product of correlation matrices. Then, if you want to evaluate one of the coordinates of our original correlation matrix, which we can then use as a distinguishing property, you can write this out or decompose this into a sum over the correlation of trails. So each of these like U's is called a mask, and they kind of define our specific trail, and so they define basically a specific coordinate of each individual correlation matrix. And what we then usually do is we take one or more dominant trails and then just kind of assume that all the other trails are small and we can ignore them. This is a heuristic that's used in linear cryptanalysis. On the other hand, we can also do linear cryptanalysis without this heuristic, where if we kind of try to prove that the correlation is 0, which is also a property we can exploit, then we often just prove that all the trails are 0 for a specific coordinate. And then, of course, the coordinate itself must be 0. Okay, then finally, the last component of ultrametric integral cryptanalysis is its new metric structure. So we will be introducing the two-adic absolute value to kind of approximate the evaluation of cryptanalytic properties. So if we take such a property, where in the case of integral cryptanalysis, you would have a weight vector, which is an indicator vector for some input set, and kind of a linear function which lifts the output bit, a specific output bit, to the rational numbers and then sums over it, then like the properties we are interested in would just be 0 modulo some power of 2. And what we can do is we can also write this out, or we can also, this is similar basically to taking the two-adic absolute value and showing that it is small. So if it's 0 modulo 2 to the nu, then the two-adic absolute value will be at most 2 to the minus nu. And so this two-adic absolute value can be defined as 1 over the largest power of 2 that divides x, at least if x is an integer. And unlike the standard absolute value that you use, it has a stronger triangle inequality, which we call the ultrametric or non-Archimedean triangle inequality, which bounds the absolute value of the sum of two numbers as the maximum of the absolute values of these numbers. Okay, so now we can get to ultrametric integral cryptanalysis. So unlike in linear cryptanalysis, we will try to diagonalize the bitwise end with a constant. And it turns out that we can do this. We can find the basis of characters, and we can find accordingly a basis on our vectors. So it turns out that this basis corresponds to the monomials on bit vectors that are then lifted to the rational numbers using the Teichmuller lift, which maps 0 to 0 and 1 to 1. But because the bitwise end doesn't form a group, we don't have kind of an orthogonal basis. So our ultrametric integral basis looks significantly different from its dual. And then indeed we can see that if we define this transition, this change of basis, we get the ultrametric integral transition matrix, and the transition matrix of the bitwise end is indeed diagonal. What you might notice is that if you take these transition matrix, the change of basis matrices modulo 2, you get the binary Mobius transformation, which then means that basically our ultrametric integral transition matrix modulo 2 is the algebraic transition matrix, which is kind of which we defined in an earlier work where we still worked over F2. So now we see that we have kind of generalized integral cryptanalysis in the sense that so it reduces back to integral cryptanalysis modulo 2, but we can express kind of more properties because we have a metric structure over, so because we're working over Q basically. So ultrametric integral cryptanalysis, so this ultrametric transition matrix has similar properties to the correlation matrix. Well, let's fix this. It's basically all the same except for the linear functions, which are no longer simple but multiplicative functions, which basically our homomorphism over these n's are still simple. Okay, so with these properties, especially the product of matrices, we can again define a theory of trails. So in this way, we get our ultrametric integral trails, and I have taken the liberty to already split it up into dominant trails. Now, by using the ultrametric, by using the two-adic absolute value, we can try to bound exactly the kind of error that the non-dominant trails introduce. Because if we bound each of these trails by some power 2 to the minus nu, so by 2 to the minus nu, then that also means that the sum is at most 2 to the minus nu. And then we basically can reduce modulo 2 to the nu and get rid of all these non-dominant trails. So this is very similar to zero correlation linear cryptanalysis in the sense that we do prove something about the non-dominant trails, and kind of in a way it's approximate zero correlation because we show that all of them are close to zero. Now, how would we do, so this is kind of all the theory, but how would we now apply this in practice? So I will get back to the example from the start and try to prove that indeed saturating this S-box gives us kind of an output bit that sums to a multiple of 4. The way we will do this is similar to zero correlation linear cryptanalysis, is in that we will do a miss in the middle technique. So we will propagate kind of our non-zero trails or large trails forward through the cipher. We will also try to propagate some trails backwards. And then in the middle, we will kind of check whether they coincide or not. And if they don't, then we have kind of approximate zero correlation. So we will try to propagate forward all the trails which are at most correlation, no, which are at least correlation 1/4, because this corresponds to property mod 4. So first we have to define our input and output property, or have to write it in our ultrametric integral basis. At the output, this is really simple, because we have this single output bit and we sum over it. This kind of directly corresponds to one of the basis elements. However, on the input side, this becomes a bit more difficult. This input set doesn't contain any minus signs, unlike, well, I'm not going to go all the way back. But so it doesn't correspond directly to a basis element, so we have to decompose it into its components in the new basis. And if we do this, we basically get that there are a few possible values, so this kind of exponents, we call them, will be all 1, or like they can all be 1 or 0, but the divisibility is, or its correlation is 2 to the difference between the original weight and kind of the weight of the trail we have. So what this means is that for us, if we propagate this forward, we ignore, of course, the first S-box because it's saturated. But if we propagate this forward, we get either 1s or 0s here, and the trails that are possible are either, or that are large enough, either have a 1 on every exponent bit here, or at least, or at most one of them is 0, which then gives you a correlation of 2 and an absolute correlation of 1/2. So now we can kind of try to propagate these forward and backwards, and we will start from the back because this is kind of easiest. All the ultrametric integral transition matrices have the kind of same first row. It's basically 1 and then a bunch of 0s. What this means is that if we take kind of the constant monomial of the output, then this propagates back to a constant monomial on the input. And so we can do this for the S-box, we can also do this for the key addition, and we can propagate like everything backwards. And then because the bit permutation is a multiplicative function, we can also use like the property that this is really simple to show that we can just kind of follow the lines backwards. And if we do this, we go all the way back, we can go all the way back to the second S-box layer, and show that basically every output bit of these S boxes has to be 0, except kind of the second one. So then we can also propagate forward. So we assume these yellow things, the yellow lines, to be 1, and that they either have weight 4 or weight 3. And kind of the first thing we notice is that we have key additions, and if we propagate a 0-bit forward through it, then kind of the first column gives us the possible transitions, and we see that if the key bit is 1, then we can also transition to a 1-bit. So kind of these black lines here kind of correspond to all different trails, which are either 0 or 1 bits. So kind of everything becomes possible. And that doesn't really matter here, but here we also have these 1 bits in our exponent. So now we can look at the transition matrix for the S box. And so because we know at the output that everything has to be 0 except the second bit, we only have to look at the first and the second and the third row. But yeah, the first row already has basically zeros everywhere, so we won't propagate forward if we just have this 1 bit. So then we look, because we all have all these possible keys, we have a bunch of columns we can look into, and we take the worst case correlation, which is 1 or -1. So we can propagate this forward, we go completely through the bit permutations, and we arrive at the second set of S boxes. Here we can do a similar argument, so we know these 3 are either 0 or 1 bits. This is a 1 bit, so if we propagate it through either 0 or 1, we basically get worst case, again, propagation with correlation 1. So finally, we end up at this S box with one specific output exponent. So we take the row that corresponds to this output exponent, and then we look at what the possible correlation of the transitions are. So from earlier, we know that this is either weight 4 or weight 3. So if this is a weight 4 input exponent, this is the only possible transition, which has correlation 1/4. So that means that this trail has correlation 1/4, so it's small. And then again, if these are weight 3, we get these green values. And worst case, this has correlation 1/2. And we already know from the input set that we had a correlation 1/2, or absolute correlation 1/2 for the trail. So in the end, we also get a correlation of 1/4. So with this, we have proven that kind of all the trails that are possible from this input set to this output property have absolute correlation 1/4, and therefore we have an integral property that sums to 0 modulo 4. This gets kind of tedious because for and present is a pretty simple example. So we built an automatic tool to search this. This is based on set solvers where we implement the transition rules in SAT. And what we find, at least on present and Simon, is that a lot of kind of the simpler properties, which are found early in the development of integral cryptanalysis, have these higher divisibility properties. However, the more optimal properties, those that have minimal data for a specific number of rounds, we don't see any improvement there. So the best application for kind of ultrametric integral cryptanalysis is in the setting where we have more data, which we get by using multiple different properties, which we can then combine also in larger properties. So that gives you more data, and then you will see higher divisibility. There are also some topics that I missed, but I think it's time to wrap up. So with this, I will quickly recap what we did. So we defined ultrametric integral cryptanalysis as a multiplicative analog to linear cryptanalysis, and it basically simplifies bitwise AND. And kind of in a way, it switches the roles of linear and nonlinear functions in that for ultrametric integral cryptanalysis, nonlinear functions are the diffusing components, while linear functions are the components that introduce confusion. So yeah, that's the work. If there are any questions, then then I will answer them gladly.